So today we'll be talking about BayesianFitForecast, an R toolbox specifically developed to streamline Bayesian parameter estimation and forecasting employing ordinary differential equations or ODE models. This comprehensive tutorial discusses everything from software installation to obtaining toolbox output using data from the 1918 influenza pandemic in San Francisco. Specifically, we will be fitting and forecasting using a variation of a susceptible, exposed, infected, recovered, or SEIR model, incorporating a reporting proportion parameter. As this code can take some time to run, I have prefit the model. Some software is required prior to running the toolbox. First, please ensure that the most recent versions of R, RStudio, RTools, and Java are downloaded on your system. Once all the necessary software has been downloaded, you will then want to navigate over to the GitHub page, which hosts all of the required files. The link to the associated GitHub can be found in the video description below. On the GitHub, you will see quite a bit of information. First, please note the folder and two files found at the top of the page. We will be downloading these to our computer shortly. Next, the remainder of the page provides a plethora of information about the toolbox, including an overview of its primary features, implementation, licensure, and suggested citation. Now, to download the required files, we will navigate to the top of the page and click on the green code icon. Once you have clicked on the code button, next please click the Download Zip button. This will download a zip folder containing all of the required code files, both for your own implementation of the software and for the example we will cover today. Once downloaded, please navigate to your respective download folder and locate the zip folder. The file should be called BayesianFitForecast main. So for me, it went to my download folder. Once you have located the folder, you will then want to unzip it. Next, open up the newly unzipped folder. For me, a new page pops up as you just saw. However, this may not be the case for you. If this is not the case, please return to your download folder to look for the unzipped folder. Once you have located the folder, you will want to click through each of the folders until you reach the License, README, and BayesianFitForecast folder. Finally, you should move the BayesianFitForecast folder to a safe place on your computer. For this tutorial, I will move it to my desktop. Once you're happy with where you have saved the folder, let's discuss the data structure and take a look at the data we will be using for the tutorial today. Once you're happy with where you have saved the folder, let's discuss the data structure and take a look at the data we'll be using for the tutorial today. The toolbox has a few requirements for the structure of input data. Specifically, the first column of the Excel file should contain numbers, starting with 0, which represent the days, weeks, years, etc. of your respective data. As can be seen with the 1918 San Francisco data here, the first column corresponds to days. However, if working with weekly data, for example, the first row would correspond to week 1 of the data, the second row to week 2 of the data, and so on and so forth. The second column of the Excel file should contain the temporal incidence data. For this tutorial, that corresponds to the number of new influenza cases on each day of the 1918 pandemic. It is important to start the second column of the Excel file with the word cases. Additionally, there are no file name requirements. So as seen here, we call this San Francisco, so we know what it is. However, the extension it must be saved under is XLSX or as an Excel file. So now that we've taken a look at the input data, we are ready now to navigate to RStudio. Well, not required to run the code, setting up an R project can help keep your working directory organized. Therefore, for the purposes of this tutorial, I will briefly walk through setting one up. First, you will want to click on the File tab in the upper right-hand corner of your RStudio page. Next, click on New Project. And then on Existing Directory. This will tell R that we want to set up our project in an already created folder. You should then see a page pop up called Create Project from Existing Directory. On this page, you will see a Browse button. Click that, and then your file directory should pop up. Finally, navigate to your unzip folder and then click Open. So let me go to that folder I just created. And then I'm going to click Open. Once you've done this, the file directory page should close and Create Project from Existing Working Directory should now show on the folder pathway that corresponds to the needed folder. So for me, I can see it's in my desktop and it's referencing the BayesianFitForecast folder. Finally, click on Create Project. Now that you have created your R project, if you close out the code and want to reopen it, click on the File button in the upper right-hand side of the RStudio page, click Open Project, and then find the project name corresponding to the toolbox code. This will ensure that your working directory is always set up correctly. Again, I want to emphasize that this is not required to run the toolbox. However, it can help keep things organized when working on multiple projects in R. Now that our project is set up, let's take a look at the contents of our working directory. So as we've set up the project, our working directory should be all in this right-hand panel down here. If you do not see that, then that means you need to go back and set up your working directory again. So again, let's take a look at the key toolbox files before we go running the code. Like I said, the bottom right-hand panel of your RStudio window should contain all of the files downloaded from GitHub. If it doesn't, you may have not set up your project correctly. If you decided you didn't want to set up an R project, to find the respective folder that contains all of this code, you can click on the three dots in the upper right-hand corner of the panel. So these three dots here, and then navigate to your desired folder and then click Open. As you can see, there are quite a few files that come with the download. However, many correspond to different examples that can be used to, that can be run using the preloaded data. So for example, all of these options files, which I'll talk about in a bit. However, right now I'm going to highlight some of the key toolbox files in their roles. First, let's take a look at diff.r. So this function is designed to identify the derivative of the variable described in the model. It plays a critical role in fitting models that involve derivatives of variables, ensuring accurate model representation and parameter estimation. Next, the metrics function contains all of the functions necessary for calculating performance metrics, such as mean absolute error, mean squared error, weighted interval scores, and the coverage of the 95% prediction interval. These metrics are essential for evaluating both calibration and forecasting performance. The ODE RHS file is used to extract the right-hand side, or the RHS, of the ODEs. This file is particularly useful when fitting the model to the derivative of the variable, allowing you to focus on the rate of change within the model. The options general use file is where you will generally be making most of your changes. This is where you can define your model parameter variables, and other key settings for running the toolbox. It serves as a primary configuration file, offering flexibility in defining the options used in each analysis. And we'll be going through this file in a little bit more detail in a bit. The run MCMC file is another file in which you'll be making changes, albeit not as many with the options general use file. And this is a file that's responsible for fitting the model to the data by estimating parameters based on the options provided in the configuration file. It is a core component of the toolbox's parameter estimation functionality. Then we have our run analysis results.r file. This generates Excel files containing the fitted model results, including forecast, parameter estimation summaries, and performance metrics. These files are saved in a folder in the output directory, allowing you to easily access, visualize, and interpret the results. Again, we will be making one small change in this file. However, we'll talk about that in a little bit. Then finally, we have our stand creator function. This generates a stand file based on the specified ODE model and parameters, enabling Bayesian inference via stand. This file automates the complex process of writing stand code, making Bayesian analysis more accessible to users who may not be familiar with probabilistic programming languages. As I mentioned before, the options general use file is a primary script where you'll be making changes. However, I'm going to take a look at the options file that corresponds to today's example. Overall, though, the options general use file provides a template to specify all required information about the data, model, parameters, error structures, and information required for the Bayesian component of the toolbox. This file can be saved with different naming schemes, as seen here, for future project-specific use. So let's close these out. And then today we'll be working with the options SCIR San Francisco example 1 file. So the first parameter we'll take a look at is calibration periods. This is where users can specify all of the calibration periods they wish to consider when analyzing a data set. It should be entered as an array of numbers where each number is selected from 1 to the total number of data points. Even if you just want to consider one calibration period, the value should still be entered as an array, but only as one element. So in this example here, we are saying we want to use a 17-day calibration period. But let's say I wanted to do a 17 and then do a 20-day calibration period, so 2 separate iterations of the code. I would add a 20 in here with it separated with a comma. However, for this example, we'll just be using one calibration period of 17. The forecasting horizon parameter specifies the horizon for forecasting and after fitting the model to the data. It is advisable to choose this number as large as possible because when generating the Excel files and results, you can then later select a forecasting horizon that is less than the first one defined when you fit the model. For example, when fitting the model by running run MCMC, if you choose a forecasting horizon of 10, as we do here, you can subsequently generate results by forecasting to any number less than 10, such as 5. This can be adjusted by changing the forecasting horizon in this file immediately after running run MCMC and before running run analyze results. The forecasting horizon can only be a positive integer. And in this case, unlike before, you just put the number here and you can only use one number. Next, the model name parameter allows you to assign a name to your project, helping to avoid any confusion when extracting results. There is no restriction on the model name that can be used, but we advise assigning distinct names to help keep different projects separated. The model name must be enclosed in double quotes. So here we're using Bayesian uniform, so we know our project is going to be called Bayesian uniform. Next, the vars parameter is where we define the variables in the model. Generally, the variables in a model are represented by the letters corresponding to the derivative taken with respect to t. When defining the variables, they should be listed in the same order as their derivatives appear in their system of ordinary differential equations. Please note each variable should be defined as a string, so enclosed in double quotes. And in this case, as we are fitting a SEIR model, we have our respective letters, so our SEIR. And then in this case, we also include a C or cumulative case state variable as well, which keeps track of the cumulative cases. Next, we need to specify model parameters. We do this with the params parameter. The parameters in the model are all letters that are not variables. The parameters can either be constants or values that need to be estimated to fit the model to the data. All parameters, whether constants or to be estimated, must be included in this vector. Please note that each parameter needs to be enclosed in double quotes. So again, in this case, as we're fitting an SEIR model, we have all of our respective parameters in the order that they appear in the differential equation or system of ODEs below, listed here. So the ODE system parameter is where we define the system of ODEs we want to work with. It includes the parameters, variables, and the derivatives of variables with respect to t. The way we define the parameters, variables, and derivatives is by writing params and then I, vars I, and diff var I, where the I at the end represents the index of the parameter or variable in the params or vars list. So for example, we have params and then 1 here, which means reference the first parameter, so reference beta. And then vars 3 here will say reference the third variable name listed, so I. And that applies for each of the params and vars seen here. And then with our diff var, this is where we have the first equation in our system is 1, 2, 3, 4, and 5, and so on. It is important to note that the first line in this string, so this is enclosed in single quotes in this case, needs to be left empty. Additionally, the last line should end with a final differential equation, followed by the closing quotation mark placed immediately after the last character of the string. So again, nothing on this line, and then the single quote immediately after the last equation here. Next, if you want to keep any of the parameters fixed at a specific value, meaning it will not be estimated from the data, you can specify this within the params fix parameter. If an element in params fix is 1, so as seen here, it means the corresponding parameter in the params parameter, so right here, is a constant. If it is 0, it means the parameter needs to be estimated. So in this example, as we have our first entry in our vector is 0, that means our beta will be estimated. As our next is 1, our gamma will be fixed, and then so on and so forth for kappa, rho, and n. So the toolbox also allows users to estimate derived parameters such as R naught and the recovery time, as comes preloaded in some of our other files. To facilitate this, we can include our desired parameters within the composite expressions list. Each entry in the list should pair the parameter name on the left with its corresponding formula on the right, expressed as a string and as a function of the model's parameters. So down here in our composite expressions list, we can see we have R0, which is our R naught, and we're saying that corresponds to beta divided by gamma. So this needs to be included within double quotation marks, and then what will happen is that when we run our code, our R naught will then be estimated. So the next two parameters, so this fitting index and fitting diff, indicate which variables the data points are related to. Specifically, fitting index is where you indicate the index of the model's variable that will be fit to the observed time series data. And fitting diff is a Boolean or 0,1 variable, which indicates if the derivative of the model's fitting variable should be fit to the data. So in this case, we're saying 5 for fitting index. So we are going to be fitting our observed time series data to our C. And that makes sense as we're working with cases, and this captures cumulative cases. And then next we're saying 1 here. So as we have 1, we're saying we want to use the derivative of the model's fitting variable to fit that to the data. So we are indicating that the derivative of the model's fitting variable should be fit to the data. So the error struct parameter is an integer that indicates the type of error structure being incorporated when fitting the model to the data. We have incorporated 3 different error structures. So 1 is negative binomial, 2 is normal, and 3 is Poisson. The error structure can be selected by indicating the respective number below. So in this case, as we've indicated error structure 3 for this example, we're going to be working with a Poisson error structure. Now we need to specify some information related to our data. So CAD file name 1 is where we define our input files. So this is the name of our file before the XLSX extension. Then we need to indicate the name of the disease or process that's related to the time series data. So we call this just San Francisco, so we know that we could call this or influenza if we wanted to. Then for date type or data type, this is where we indicate what type of data we're working with. So either cases, deaths, hospitalizations. And then our date type is where we say, are we working with days, weeks, and years, so on and so forth. The last bit of parameters we're going to discuss relate to the Bayesian estimation features of the toolbox. So let me pull those up. First, we must provide information related to the prior distributions for our parameters. If a parameter is fixed, meaning that the corresponding location in params fixed is 1, the prior should be defined as a constant value, meaning it should be a real number. So in our case, that will apply to our gamma, kappa, rho, and m. If a parameter needs to be estimated, a distribution must be entered as a string, so within quotation marks. And for us, that applies for our beta, as we are planning on estimating that. Various types of distributions can be used. You should define the priors for all parameters that are listed in params, and the order in which you enter the parameter priors must match the order in params. We can also specify information related to the upper and lower bounds for estimation. And if there's no upper bound for the data, we can specify that as an NA. So in this case, you can see we have set values for those 4 parameters which we're fixing. And then we also are saying for what we're estimating for that first parameter, we're going to use a uniform distribution with a lower bound of 0 and an upper bound of NA. So we're saying there's no upper bound. So in this next section, if you've selected either negative binomial or normal error structures, we need to estimate an additional parameter. Therefore, we must also specify an error structure prior to distribution. To do so, we follow a similar pattern as discussed for the model parameter prior specification. However, if working with a negative binomial distribution, we need to name our variable negative bind error prior, so as seen here. If working with a normal distribution, we need to name our variable normal error prior, as seen here. It is important to note that if the error structure is equal to 1, then only the negative bind error prior needs to be specified. And normal error prior will not play any role in fitting the model. Similarly, if its error structure is set to 2, So we tell it we want to use a normal. Then we say only the normal prior needs to be defined and the negative bind prior will not be used. As we are working with a Poisson, neither will be used or come into play at all. Next, if the initial conditions need to be estimated, we can then specify this within our var's initial parameters. So if var's init equals 1, as it does in this case, the initial conditions will not be estimated and no other changes to our code are needed. However, var's init equals 0, the initial conditions will be estimated and additional adjustments are necessary. And additional details on all of the steps that can be followed when that is the case can be found within the tutorial manuscript. Next, we need to specify the initial conditions of our state variables. We do this within the IC parameter, and the order of the initial conditions should align with the order of the state variables specified earlier in the var's parameter. So as you can see here, we have our initial conditions for the parameters. Or I'm sorry, initial conditions for our state variables. Finally, we need to indicate the number of MC steps and number of chains. We do this within the neater and num chains parameters respectively. So here we're using 1,000 MC steps and then using 2 chains. Now that we have made all the necessary specifications, we now need to reopen the run MC file. The only change that needs to be made here is in line 5. This is where we specify the name of our options file, including the R extension. So as you can see here, we have our EX1 already specified. However, if you're working with another example or your own options file, this is where you would make that change. Just make sure you have the .r at the end and everything's within double quotes. It is important to note that if this is the first time you are running this code, you may have to download quite a few packages at this step. However, R will walk you through this process and prompt you if your packages need to be downloaded. Additionally, please ensure that you have R tools downloaded, otherwise this step will not run properly and you will receive an error. I have already run this portion of the code as it does take some time to run. Therefore, I will not do so again. However, to run all of the code at once, you can either highlight all of the code and then click Run, or click Control, Shift, and Enter at the same time on your keyboard, and that should run all of the code. After running Run MC, the samples will be generated and an R data file will be saved in the same directory as the rest of your files. For each calibration period in the calibration periods array, there will be a corresponding R data file. Therefore, as we only have one calibration period for this example, you should only get one calibration period file or one R data file. This file is necessary to obtain figures and other data related to our model fit and forecast. So as we can see down here, this is the R data file corresponding to this example. We have our Bayesian uniform, so that's the model we specified in our options file, 17-day calibration, a 10-day forecast. We're working with a Poisson error structure, and then that's the name that we specified for our cat or our disease. And then we have our R data. Finally, we can open up the run analyze results file to obtain usable output. Similar to earlier, we only need to change one line, in this case, line 10. So let me open up the file. And then here's line 10. So we just need to change this to match our options file. Once this has been done, we can then run the code. So let me get this running. This runs a lot faster than what we were just talking about. From this, we obtain quite a few files to our newly created output folder. And you can see it's already done running. You can ignore these warning messages. And then one thing to note here as well, this is where you need to make sure you have the most recent version of Java updated, or most recent version of Java. So let's go take a look at our options file. And before we do that, we do need to make sure that we close out R. So let me close all this out. And then terminate R. And then I'm also going to close it out manually. So let's now go take a look at our output. So as you can see here, we get an output folder that's created. And then within the output folder, we get different folder names. So in this case, we have our Bayesian uniform, San Francisco, Poisson, calibration period 17, and forecasting 10. So this file name is pulled from a lot of that information we specified in the options file. Then within here, you can see we have quite a few different file types. So we have 4 Excel files. And first we have our convergence. Ooh, apologize, my computer's acting a little funky. So we have our convergence file with a preview shown here. And this file includes the convergence parameter r hat. It is recommended to use Bayesian inference whenever that parameter r hat is less than 1.1. To achieve this goal, you can increase the NITER or the number of iterations. So just more iterations when r hat is less than 1.1. Next, we have our forecast file. This file includes 5 columns, our date, data, median, lower bound, and upper bound. And this is where we can plot the actual forecast we obtained. And as we use a 17-day calibration period, this is what we calibrated our data with. This is the model fit, so that median, lower bound, upper bound. And then this lower part here is our forecast. So we have our forecast for our median, our lower bound, upper bound, and then what actually happened during that period. We then get our parameters file. So this is a file that provides an analysis of the parameter estimation by giving the median, mean, lower bound, and upper bound of all the parameters. In the case of using a normal error structure, the parameter sigma, and in the case of a negative binomial error structure, the associated error parameter will also be estimated here. So in this case, as we used Poisson, we don't have any error structures. And as we're only estimating beta, we then get the parameter estimations, our median, our mean, our lower bound, and our upper bound. The final file we get is our performance metrics. And this is a file that provides 4 performance metrics for both calibration and forecasting periods. So our mean absolute error, mean squared error, weighted interval score, and 95% coverage. And we can see these values here for our calibration and forecast. And we also get some PDF files that are generated within the folder that contain different figures. So first, our histogram. So we get our beta and our R naught histograms. And these are the histograms of the estimated parameters that will be saved. In the case of a normal error structure, we'll also get the histogram for its error parameter, and similarly for negative binomial. And in this case, as we did have a composite expression R naught, we also get the histogram here. So we get it for our beta and then our R naught. We then get a forecast plot. So this is a plot for fitting the model and forecasting. And it shows the median fit and the 95% PI. So we can see our fit here and then our forecast. And as you can see, the 95% PI coverage for our forecast isn't great. Then we also get our posterior chains. And then our trace plot. Which unfortunately is not loaded. Let me see if I can get that to work. Apologize, my computer's acting a little wonky, but we also get a trace plot as well. So that is the gist of the Bayesian Fit Forecast toolbox. As always, if there are any questions or concerns, please do not hesitate to reach out. Thank you for listening.